Start. First thing we're going to talk, we hit a little bit on consistency last week, but I want to cover it a little more. So just the basic concept is, say we have a matrix, an augmented matrix, something, something, and then on the bottom we have 0 row. If all these guys are 0, then this one also must equal 0. And the reason for that is this is basically saying 0x1 plus 0x2 plus 0x3 equals the box. Okay, so what does that mean? So there are a number of different types of problems you might get that relate to this. So I'll go over an example. So this is 1.3.24. So he actually went over this a little bit in the lecture, but I want to take it a step further than he did, just because I think it's a really good problem. So if we have x1 plus 3x2 minus x3 equals b1, x1 plus 2x2 equals b2, and 3x1 plus 7x2 minus x3 equals b3. So if we write our augmented matrix, this just becomes 1, 1, 3, 3, 2, 7, negative 1, 0, negative 1, and then b1, b2, and b3. And the question is, how do we set our values of b1, b2, and b3 so that this system of equations is consistent? So basically, we're going to need to make sure that if it's linearly dependent and we have a 0 row, we need to make sure it's 0 on both sides. So how do we do that? Let's go ahead and get to our reduced echelon form. So let's do row 2 minus row 1. Top and bottom will be the same. And then we're going to have 0, negative 1, 1, and b2 minus b1. So then let's go ahead and do this next thing. So row 3 minus 3 row 1. And that'll give us first 2 rows the same. And on the bottom, we'll have 0, negative 2, 2, and b3 minus 3b1. Okay. So then the last step to get to where we need for the consistency condition is, let's just do row 3 minus 2 row 2. And we'll notice that sorry. When we do this, we'll end up getting 0, 0, 0, and we'll still have b3 minus 3b1, and then we'll be also minus 2b2 plus 2b1. So we'll notice that we have a 0 row, and then we have this long equation over here. So this is what's called our consistency condition. So we have the b3 minus b1 minus 2b2 equals 0. So in order for this system of equations to have a solution, this consistency condition must hold. Okay. I'm going to go ahead and go one step further here. So I'm going to do row 1 plus 3 row 2, and I'm also going to do negative row 2. You'll see why in a second. So this will give us our reduced echelon form. 2, negative 1, 0. Okay. So now we have our reduced echelon form. And then the problem is it says if we have a few different sets of data, so we're going to do two examples. So first, let's say b equals 1, 1, 3. It says, um, is there a solution? And if so, basically, what is it? So we can tell if there's a solution, so we can plug those values in, and we end up getting 1 or 3 minus 1 minus 2 equals 0, and that does check out, so there will be a solution to this set. And if we plug in to our equation over here, if we plug these b values in here, we get 1, 0, 0. So this basically means that x1 equals 1 minus 2x3, x2 equals x3, and x3 also equals x3. So if x3 is our free variable, then x2 and x1 are both our constrained variables. Okay, and we could choose any values for those, and it'll be a solution to this system. Second example is b equals 1, 0, negative 1. So plugging in once again, we get negative 1 minus 1 minus 0 equals negative 2, and that does not equal 0. So there will be no solutions at this point. So if we plug 1, 0, negative 1 into our equation, we will not get an answer. So that's basically an example of checking for consistency. Does anybody have any questions on that? Or is that pretty clear? Okay. Okay, so if there are no questions there, then we'll go ahead and move on to the next couple topics. So next things we'll talk about are some basic matrix algebra calculations. So first thing we'll go over is addition, and this will be pretty straightforward. So matrix addition is really easy. So let's say A11, A12, A21, A22. So if we were to add these two matrices, we would just be adding the elements. So it's this guy plus this guy plus this guy, and you just add the elements in the exact same spot. So A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. So you'll notice that in order to conduct matrix addition, both matrices will have to be the same size. Okay, so let's just do a quick example. So 1.5.3. So if we have A equals 2, 1, 1, 3, and B equals 0, 1, negative 1, 3, then let's find D such that A plus D equals B. Okay, so just like with normal addition, we can rewrite this as D equals B minus A. So D equals 0, 1, negative 1, 3, minus 2, 1, 1, 3. And that's just going to equal 0 minus 2, negative 1 minus 1, 1 minus 1, and 3 minus 3. So D is going to be negative 2, 0, 0. So that's it. That's matrix addition. So really, really straightforward. Anybody unclear on that or pretty solid? Okay. So everybody's solid on that. So now a little less intuitive is matrix multiplication. So we'll talk about that now. So matrix multiplication, if we have a matrix A times a matrix B, then the ijth entry is going to equal the ith row of A times the jth column of B. And basically, you can kind of think of it, it works the exact same as a dot product. So the dot product is a row vector times a column vector. So what does that mean? So if we do an example, so let's look at 1.5.31. We have A equals 2134. B equals 1124. AB is going to equal the product of these two matrices. Okay, and how do we do that? So you take the dot, once again, the dot product of a row times a column. So if you look at where they intersect, that's going to be the point on the matrix. So you see that these are the first row and the first column. So we look at 1, 1. So 1, 1. So the 1/1th position is going to be 2 times 1 plus 3 times 1. 2 times 1 plus 3 times 1. Now if we look at the bottom position, so we have 1 times 1 plus 4 times 1. And then if we do the first row by the second column, that's 1, 2. So the 1/2th position will be 2 times 2 plus 3 times 4. And similarly, we're going to have 1 times 2 plus 4 times 4. And if you do all this addition, we'll just get 5, 5, 16, and 18. Now notice if we do BA, we will not get the same answer. So this process is not commutative. So doing the same thing, we get 1 times 2 plus 2 times 1. We get 1 times 2 plus 4 times 1. And then we get 1 times 3 plus 2 times 4. And 1 times 3 plus 4 times 4. So just rows by columns. And this will give us 4, 6, 11, and 19. So we can see that we end up getting very different answers. So these are not commutative at all. Okay, so a few traits. So when we're doing this multiplication, so if we have an m by n matrix, and we multiply that by an n by p matrix, so row by column, then you'll notice that these two numbers have to be the same. And the reason is, so if I have taking a dot product, then if I do a row times a column, the number of column entries will have to be the same as the number of row entries, or else I can't do that operation. And then when I do this, the result will be an m by p matrix. So in the end, I'll end up having a so if this is, even if it's just if I do a 10 by 1 and I multiply it by a 1 by 10, then I'm going to end up with a 10 by 10 matrix. Even though I just started off with a column vector and a single row vector, the result will be a 10 by 10 matrix. So you can definitely up the dimensions of the matrix fairly quickly. Okay, and then another trait, so now that we know some basics on matrix multiplication, and we can see that our setup for the equations will actually end up being, so if we do the multiplication of these two matrices, we have A11 times x1 plus A12 times x2 on the top, and we have A21 x1 plus A22 x2 on the bottom. And that is how we get our basic equations. So then this looks exactly like our system of equations that we would start with, that we formed our matrices out of. So that's why we write the matrices how we do. Does that make sense to everybody? The matrix multiplication. It's a little weird when you first see it, but it's not too difficult. So, okay. All right. So then, another thing that we kind of get out of that is we can write answers to a system of equations in something that's called vector form. So let's look at 1.5.43. We have this problem. So it's in reduced echelon form. And we've been writing it as x1 equals -2 plus x3, x2 equals 3 minus 2x3, and x3 equals x3. So that's how we've been writing our answers. But we can write it another way, and that's just as column vectors. So if we have x1, x2, and x3, knowing what we know about matrix addition now, we could also write this as -2, 3, 0. So you see I just took the scalars out of here, the ones that are by themselves. And you can write that plus 1, -2, 1. So I just took the coefficients in front of the x3 times x3. So this is another way to write the answer, and this is actually what you'll see more commonly now in the book after the section where you learn about some of the basic operations. Okay. Does anybody have any questions on any of that? Okay. All right. So moving on, the last kind of major matrix algebra thing I'm going to talk about is the transpose. So if we have the transpose of a matrix, so let's say A equals A11, A12, A13. Okay. Then the transpose, we're just going to switch I and J. So basically switch the rows and columns. Okay. So A transpose, so A11 is going to stay in the same place. A22 is going to stay in the same place. But everybody else, so A21 is going to move from the second row first column to the first row second column. A12, similarly. So you see that everybody just flipped over their mirror image, basically. So that's what a transpose is. And you'll see those a little more when you're doing some operations with inverses, especially, and when you're taking some derivatives of matrices. That's when you'll see it more commonly. But let's do a quick problem. So 1.6.42a. So let's see, b equals 1134. C equals 2435. And we're going to find A such that A transpose plus B equals C. So this is very similar to the basic addition problem we did earlier. So if we look at this, so we get A transpose plus B equals C. So A transpose is going to equal C minus B. So looking at that real quick, we just get 2 minus 1, 3 minus 3, 1 minus 4, and 4 minus 1, sorry, and 5 minus 4. That will be 1, 0, 3, 1. So remember that's A transpose. So if A transpose equals that, then A is just going to equal flipping the rows and columns. We get 3, 0. That's going to be our A. So transpose, nothing too complicated, but it's kind of a new idea. So just make sure you're familiar with what that means. Okay. So I wanted to go over that set of things real quick, but now we're on linear independence. So linear independence, this is going to be what the quiz is on next week. Let's talk about this briefly. And I'm trying to keep it to kind of the section that we're on in the book. So Andrew shot me an email basically saying that there was another way to find out if a matrix is linearly independent, but the definition in the book as of right now. So if we have V1, so this is a set of vectors. So if we have a set of vectors, we say that they are linearly independent if the only solution to the vector equation A1 V1 plus A2 V2 AP VP 0. So if the only solution to this is the trivial solution, okay, and just a reminder, what is the trivial solution? So the trivial solution is just the zero vector. So if A equals 0, 0, all the way down to 0, however many it is. So basically what this is saying is the only way to make a linear combination of all these vectors equal to the zero vector is if they're all 0. And then what does that mean? What it means is that there's no way of combining any subset of the vectors to create another member of the subset. There's no way we can take V1, V2, V3, V4 and add them up with any scalar multiples to create VP. So that's what linear independence is. And if it's not linearly independent, so if this is not true, then it's linearly dependent. Okay, so how do we prove this? So this is what's called a characteristic of linear independence. So this is something that must be true in order for the set to be linearly independent. We'll see a little later that if this is true, then the determinant of the system of the matrix created by the column vectors will also be 0. But we haven't learned determinants yet, so we'll hold off on that for just a second. Okay. So to check this, we take the set of column vectors and we create a matrix from them. So we have big V equals this set. We multiply it by an A vector, set it equal to the 0 vector. Then we have to check, and if the only solution to this equation is the 0 vector for A, then it's linearly independent. So we'll do a couple examples. So I'm going to do one example where it's linearly independent and one where it's linearly dependent, so we can kind of see both sides. So first, if we have 1.7.1, so V1 equals 1, 2, V2 equals 2, 3. So is the set V1, V2 linearly independent? So that's our problem. So let's create our vector. So V equals V1, V2. That's going to equal 1, 2, 2, 3. So our problem becomes 1, 2, 2, 3 times a1, a2 equals the 0 vector. Okay, so this is a very easy problem to solve, so let's just set it up as an augmented matrix. And we end up getting the second row minus the first, multiply the bottom row by -1, and then we can add 2 times this row to this row, and we end up just getting 0, 1, 0, 0, 1, and 0, 0. So we can see that x1 equals 0, or a1 equals 0, and a2 equals 0. So since both have to equal 0, this is the trivial solution. So they are linearly independent. Okay. Now another example. So let's do 1.7.11. So u1 equals 2, 1, -3. u2 equals 4, 4, 0. And u3 equals 1, 1, 0. So is the set u1, u2, u3 linearly independent? Okay, so let's check it. 2, 1, -3, 4, 4, 0. Let's make an augmented matrix. So we're setting this equal to 0. And we end up getting switch the first and third rows and multiply the bottom row by -1/3. So we get 0, 0, 0, and 2, 4, 1, 1, 4, 1. And go ahead and subtract 1 times the first row from the second equation and 2 times the first row from the third. End up getting 0, 0. And then subtracting the third row from the the second row from the third row. End up getting and just getting it into reduced echelon form. Okay, and we can see here that x1 equals 0 and x2 equals -x3/4. So this means that they're linearly dependent. Because there are going to be infinite number of solutions to this problem. So anything we plug in for x3, we just choose the corresponding value for x2. And there we go. So we can see that if we were to choose -1 or -4 for x3, then x2 would equal 1. And what does this basically mean? This basically means that we multiply u3 times -4, and we can see that that is -4, -4, 0. And if we add that to u2, it equals 0. So you clearly see that u3 is dependent on u2, or u2 is dependent on u3. Either way, but you can multiply a constant times either one of these vectors and you get the other one. So that's what we mean by linearly dependent. So this vector is linearly dependent on this one. This one's linearly dependent on this one. When we did our first set, there's no way you can multiply either one of these vectors times a constant to get the other one. So that's what we mean when we say linearly independent. Okay. Does that make sense to everybody? So it can be a little strange when you first learn it, but it's nothing too complicated. But once again, there's a lot of topics are getting introduced. Okay. Okay. All right. So now that we've talked about that, we're going to talk about a very similar topic. So linear independence is kind of goes hand in hand with singularity. So what is singularity? So a matrix A is singular or is non-singular, sorry, non-singular if the only solution to ax equals 0 is the trivial solution. So we can see that we're going to check this basically the exact same way that we check for vectors. So, but the difference is in linear independence, we're talking about a set of column vectors. Here we're talking about a matrix. So if the columns in matrix A are linearly independent, then A is non-singular. Else, A is singular. So if the column vectors are linearly dependent, then it is a singular matrix. Okay. So I'll go ahead and write that out. So if column vectors A are linearly independent, A is non-singular. Okay. So that's an important kind of connection to make. So singularity, linear independence, very important. So basically what we're saying, if you have a linearly independent matrix, then you will be able to find a unique solution to a problem. If you have a linearly dependent matrix, then you will have infinite solutions to a problem if there are any solutions. So you'll either have no solution or infinite solutions. So they kind of go hand in hand. You'll see that a lot more as you go into some of the practice problems. Okay. So what are some basic traits of a singular matrix? So one important thing, so if A, in addition to being able to find that unique solution, if A is non-singular, then it has what we call an inverse. So when we're doing basic multiplication, so if I have the number 5, then I know that the 5 to the negative 1, so the inverse, the multiplicative inverse, so it's what is 5 multiplied by to get 1. And that's what that is. That equals 5 over 5. So that's what we mean by a multiplicative inverse. So a matrix multiplicative inverse is, let's say we have a matrix A. So it would be the inverse. We multiply those out, and we get called the identity matrix. And the identity matrix is basically this matrix, and it has ones on the diagonal, and everything else is 0. Um, and so we need to find this guy, and you'll notice that if you do find that inverse, then there'll some cool properties that kind of follow up on it. So some things about the multiplicative identity. So just like if we were to take 5 times 1 equals 1, if we were to take A times I, that is going to be equal to I times A, which is just going to be equal to A. So if we multiply any matrix by this identity matrix, it's just going to equal itself. So that's what we mean. That's why we call it an inverse. So it's very similar to multiplicative inverse with multiplicative identity with scalars. Um, we're doing basically the same thing with matrices. And this is useful because if we have our basic equation, then if we were to rewrite this as inverse times A, and we just multiply both sides by the same thing, then you'll notice that this is going to equal the identity matrix, so that we end up getting x equals to A inverse times B. So if somehow you did know the inverse of a matrix, then instead of going through any of our row reduction processes, you can just solve it directly. You can just say x equals the multiplication of A inverse times B. So it kind of makes things a little bit easier if you have the inverse, but we'll learn a little later that finding the inverse is often more trouble than it's worth. So you won't actually see that much when you're doing numerical solutions. So when you get to numerical computing in a year or two, you're going to have kind of a different problem set to deal with. Okay, I went a little bit quick today, but that's actually all I wanted to cover this week. Um, so we went through linear independence, so hopefully you're good to go on the quiz that's coming up next week. Did anybody have any homework problems that they were having issues with or that they wanted to go over? Or which could use some clarification, or any topics that needed a little bit of clarification? Okay. Um, well, if not, then have a great weekend, and hopefully you're staying safe at home. And I will talk to you next week.